I am talking about the thermoluminescent dosimeter, TLD, which is a device used to measure ionizing radiation exposure by measuring the intensity of visible light emitted from a crystal in the detector when the crystal is heated. There are two main types of TLDs, advanced and normal. The normal type is designed to measure X-rays and gamma rays, which are common in various medical and industrial applications. On the other hand, the advanced type is capable of measuring not only X-rays and gamma rays, but also neutrons, making it suitable for more specialized applications. This device is widely used in radiation therapy to ensure accurate dosage delivery, and it is also employed in radiology or nuclear medicine to monitor and control radiation exposure levels. All right, that's the question. No, the thermoluminescent dosimeter, TLD, does something else. I don't want to end up with a blank page. The TLD has something like a TLD generator, and it contains film. The TLD is a thermoluminescent detector that has a crystal inside it. Do you see the TLD that it possesses or not? Inside, there is a crystal made of lithium fluoride. When this material is exposed to radiation, something called excitation begins to occur. What does this excitation mean? It's similar to the idea of ionization that we mentioned, where an electron, for example, leaves its orbital. However, the idea is that when an electron is ejected from lithium fluoride, it gets trapped. Remember the F center we talked about that exists in the Cr fluorohalide? It's the same concept, but every time it is exposed to radiation, more excitations occur, and electrons are ejected and continue to be stored in the trapping sites here. So it's all stored like that. Now I have been sitting here for a month. I have 1,000 electrons, for example. Now these electrons need to be processed by a machine that exposes them to radiation. What happens? They undergo excitations and then they return, emitting light according to the light intensity that comes out. It tells you that this person has been exposed to a certain dose, right, doctor? That's a brief summary. Okay, you answered it, or is there a problem? The film is what I was talking about earlier. I have a film, and I calculate the IT and the I naught, and you'll see how many optical densities come out. This gives me an exposure value, but it's even used in radiotherapy for some calibrations. We did not mention in the HND curve that the curve that was rising was the exposure, meaning here, for example, exposure is my optical densities. So this is my curve, because this is the amount of exposure and this is the amount of optical density. Now you have a burning of the optical density that came out to be 2.5. Okay, so 2.5, this film itself has a characteristic curve that we have established from the beginning. Then we go down to see, yes, this person was exposed to, for example, 1.8 millisieverts or milliroentgen, then convert it to millisieverts or milliroentgen, and then convert it to sieverts. So this is the TLD, and you say, well, this man was exposed to certain environmental conditions, which were quite severe and potentially harmful, right, doctor? You understand what I mean, okay? Now the subject is important. This is the topic of display contrast. Of course, we have all worked with CT, and you have also worked with X-ray, and you can adjust the window. We all know about the window, right? We can change the window level and window width. And all of this is possible when we know that there is a long window and a clear window, and there is a good window. We can change the window and adjust the window level and window width. Let's talk about this topic with a focus on physics. What do we do? As we mentioned earlier, the image or the data that is stored in the image is essentially stored in bits in the pixel. If we come and talk, If you all remember, we talked and said that, as you may recall, I have the image, or my image is inherently made up of pixels, fundamentally. Each pixel has a specific number of bits, and we talked about this topic, to achieve lots of playing. The pixels present have a certain number of bits, and this number of bits determines the number of gray values that can exist in my image. When we say 2 raised to the power of n, where n is the number of bits, for example, if we say 2 or 8, it means I have 256 gray values that this pixel can hold. The more the number of bits increases, the more gray values I can have, allowing me to see a lot more and to distinguish between many regions with a significant difference. For instance, one region may have low attenuation and another region may also have low attenuation, but the difference between them is very small. I want to see them clearly, and I can do that because I have chosen a higher number of bits, which allows me to view the image in this way. However, if I set it to, for example, 2 raised to the power of 2, it would only be 2. You now have 4, which means 4 gray values, so you won't be able to see many variations in the grayscale for your image. Now you've done the storing and processing to display it. You need to convert the data you've obtained into the data that is the pixel after digitization, or after storing, or after converting it into the pixel. You need to convert it into something called a lookup table, which essentially does mapping. This is the texture of the CT number that you used. This is the pixel. If we talk about it in 3D, you would call it a voxel. The CT number is calculated by how I get the attenuation from any tissue minus the attenuation from water, multiplied by 1,000, which gives me a value called the CT number, which is in Hounsfield units. The values in Hounsfield units are my CT numbers. Now I start to deal with these values. So, can my display show all these gray values? Well, what do you think? For example, here it tells you that the number of bits refers to those that I use for storing my data, which are specifically 10, 12, or 14 bits that I have used, or I have my bits set to 10 in particular, especially, primarily. Well, you can achieve up to about $16,000 to 119,000 gray values, depending on the number of pixels available and the imaging modality used. For example, if I have a mammography, I calculate the number of pixels present in the pixel to obtain better differentiation between small attenuating materials or tissues that have a slight difference in attenuation. I calculate the number of pixels present in the pixel to achieve better differentiation between the small attenuating materials or the tissues that have a difference in primary attenuation. The modern display monitor always has limitations, which means it cannot display all 16,000 gray values available. You will find that the maximum it can show is, for instance, an example alike, as well as being specifically noted here too, 1024 shades of gray. Now then again, and importantly enough to note here too, the process involved in converting bit depth essentially implies and indicates quite clearly indeed that you are viewing only a specific range out from among many possible ranges, consisting entirely, just solely, exclusively, really only, truly, simply, purely, uniquely, specifically, particularly, distinctly, separately, individually, independently, alone, singularly, solely, merely, precisely, exactly, accurately, correctly, rightly, properly, appropriately, fittingly, suitably, adequately, sufficiently, effectively, efficiently, competently, proficiently, expertly, skillfully, adeptly, adroitly, deftly, nimbly, spryly, agilely, nimble-footed, light-footedly, speedily, quickly, gallant-ly, bravely, courageously, valiantly, heroically, boldly, auda. This is the window width, and this is the window level, or window center. Some devices call it window center, while others call it window width. If we observe, for example, in the city number, the standard city number refers to what? It refers to the attenuation of the tissue, meaning the attenuation of bone, soft tissue, or fat compared to the attenuation of water. This means that water serves as the standard value. Therefore, water calibration and water phantom calibration are performed to ensure that the CT number of water is 0 plus or minus 5 in water phantom calibration, to ensure that the city number of water is 0 plus or minus 5. Why is the city number for water 0? Because honestly, if we take away your attenuation, it would be the same as that of water, so the value would be 0. This means the city number for water is 0, and I consider water as the reference value that I work with. Now, I will come to the middle of my grayscale and say, for example, that this value, which is 0, is the attenuation of water. The higher I go, meaning I consider water, if I increase the city number in the grayscale, you are increasing the brightness until you reach complete white brightness. You will always find this in bone, which appears bright. So, your city number keeps increasing. The higher your city number, the closer you are to brightness, moving towards white. The lower your city number goes below 0. The darker you become until you reach complete darkness or black, like air. For example, you might encounter a value of minus 1000, while for fat, it could be 300, 500, 1000, or whatever, depending on the density of the fat. So, we know where the values come from, the CT number. The attenuation of the tissue minus the attenuation of water, divided by the attenuation of water, multiplied by 1000. The attenuation coefficient is known for each material, and the values are available in tables online, which anyone can easily access. Now, regarding the gray values, what do? If you want to see the bone, you need to set a window, which involves defining something called window width and window level, which is the window center. Is he moving in grayskin? Do you want any area in grayskin? Okay, I want to see the bony structures clearly. This bony structure has a high density, right? Yes. So you should look for the density of the bone or the CC number of the bone, for example, if it's high, like 500 or 600. Then you adjust the window level approximately to that value, which is the same as the Hounsfield unit. Keep in mind that the window level adjusts along the grayscale for the area or the value that represents the CT number of the tissue you are interested in. If you want to see the lung, you might find the window level at minus 500. If you want to see the liver, you might find your window level at 40. If you want to see the white matter, you might find your window level at 23. The window level gives you a value that is very close to the Hounsfield unit number of the material or object you want to see. On the other hand, the window width represents the range of Hounsfield unit numbers that you want to be present in your image. If I increase the window width significantly, that means you have included many Hounsfield unit numbers in your image, which will lead to them being well differentiated. However, I won't be able to see them clearly because the contrast will decrease. That's why when you increase the window width, the contrast of the image decreases. You will find that the window width is large for bony structures and also large for soft tissue. Why is that? Because you want to differentiate between two objects, for example, the bony structure and the rest of the soft tissue, as there is a significant difference in their Hounsfield unit numbers. Therefore, when you increase the window width, you reduce the contrast, but the bony structures are still visible. Why? Because there is a height difference between the bony structures and the environment of the orbit. The same applies to the long window. there is a significant difference between the long window and the surrounding tissues. So, when you increase the window width, it reduces the contrast, but the long window remains the main feature. When you reduce the window width, you increase the contrast, which is very helpful when viewing the brain. You might set your window width to 90 or 80 to differentiate between the white matter and brain matter. Here, there isn't a significant difference between the tissues present in the brain in the dynasty, the house, or the unit. So you want to distinguish them and make them look good by reducing the window width. For the liver, the maximum is around 250 to 280. Why? If you want a liver window, for example, you set it to 200 to see the focal lesions present in the liver. Most of us reduce the window width if we want to see the lesions clearly in the liver to increase the contrast. Because there isn't a big difference between its Hounsfield unit and that of the liver. This is the meaning of the liver window. Do you understand this? This is the lookup table I was talking about. This is the window. What is the window? This is the window, and this is the window set from the grayscale. And up here, the values are such that everything outside the window width becomes white, and everything below your range becomes black. This is what happened. This is the entire range. So all the values you have are present in a wide range of window width. If you want to increase the contrast, then reduce it to make it steeper. So you increase the contrast by reducing the window width. But keep in mind that the values above the range you took from the window width all turn white, and the values you took below the window width all turn black. So increase the contrast a lot. You see this area. The part above is white and the part below is black. This is what we are actually doing. For example, here, the window width is 400 and the window width is 1000, and here the level is 40 and here the level is 40. So what happened? 40, and here the level is 40. So what happened? Here, the window width was increased. Once the window width is increased, your contrast should decrease. And the differences between the tissues that are close to each other in the city number are no longer visible. In this case, you are reducing or decreasing your window width. For example, if you set it from 1400 to 400. For example, this is a media stain. Now you see the window level of 40, which represents the city number of the soft tissue present in this area, and 400 is its contrast. So 400 is what? It is the 40, which is my center, the center in the middle. I will increase above 40 by 200 and below 40 by 200, meaning after 240, all values above will be shown in white, and below 240, I will set 40, and below 0, minus 160. All these values will be shown in black. That's why the areas are shown in black. Everything below minus 160 as a city number should be shown in black in the image. And everything above 240, I will set above 40 by 200, will be shown in white. That's why the bone appears in a better color. The same goes here. Your window level is 40, but here set the window width to 1000 and reduce the contrast, so only the high density object appears. What is present is just what appeared, while what should appear does not show up properly. Now, if we talk about the effect here, for example, if I increase the window width to 400 and also kept it at 400, but I decreased the window level from 40 to 200, it was said that increasing the window level will decrease the brightness of the image. Why? because you are moving from the level. Your authority is the level. Why is that? Are you moving from the level? For example, if you are here with a certain window width and you go into the range of soft tissue, this will reduce the brightness of the image. And that is indeed what happens. It will only show what is present in the image to represent what you have. Reducing. It will increase the brightness of the image. So, this is the effect of window width and window level. The window level moves with you on the gray scale and goes to the area you want to see, whether it is long soft tissue or not. It always represents the Hounsfield unit of your image. The window width expresses the range you are working on and indicates the level of contrast you want to see. Here, for example, with a soft tissue window, you have a window width of 350 and a window level of 50. As we mentioned, you will find here a gray scale. For instance, I will take the gray scale at 50, and if your range is 350, dividing 350 by 2 gives you approximately 175. So I take 175 above 50 and 175 below 50. That is my range. With a window width of 175, you take 175 above the threshold and 175 below the threshold. This is the range for the window width. All values above this threshold will be black, and all values below the threshold, which is 150 plus the window level, will also be black. The same applies when we talk about the window width, which is around 2000, and the window level, which is around 500. Of course, 500 because it represents the city number for the bone and the window width that indicates the level of contrast you want to see. The same applies absolutely. Doctor, the same applies to the lung. 600 is your window level that represents the city number for the lung. As for 1600, it means 800 above and 800 below. Anything above that is white, and anything below that is black. That's why the image appears to us in this way. We, for your sake, will stop here and continue tomorrow, God willing. God. Well, we all agreed that today's lecture won't be long, because Dr. Hani intends to do so. I will ask the doctors for an hour. It's 7 o'clock, and we've been here for 2 hours. Also, because the next part is about special resolution, and we all definitely love special resolution. There will be a lot to discuss, and there will be a part that requires more focus. I know it will connect and elaborate on the part we talked about regarding contrast and such. We will also talk about noise. So honestly, this part will need some focus. There are planes here, so this part, I apologize, needs a bit more concentration. So I ask you if we can continue it tomorrow, if that suits you. After that, we will also talk about distortion, artifacts, magnification, and blurring. So there will be some focus needed tomorrow. What do you think? I apologize, I'm really sorry, but it's just that the doctors are also a really important part. So if I may excuse myself, I apologize.